Hi everyone, welcome to my first lecture video. It's my hope that by putting the lecture notes on videos and having you watch them outside of class that we can free up some time for demonstrations and more discussion and labs and activities and all the fun stuff that makes physics worth learning in class, and get kind of the basics, the notes part, the content part, get some of that done outside of class. I mean, I'll still obviously be helping you in class when we have something to do, but this should allow us to do some more of the fun things that I've always wanted to do. Okay, so that's why we're doing this. So, let's get started. What is physics? You guys are in Regents physics watching this course, or watching this video. What is physics? It's not really descriptive. I mean, chemistry kind of tells you that you're going to be working with chemicals. Everyone kind of knows what biology is. Everyone knows it's about living things. Earth science, that's very self-explanatory, but what is physics? Okay, what does that mean? You can see the root word physical in there, but that doesn't really help us much. I would say that physics is the study of the entire natural world. Really, the universe, okay? Physics is the study of the universe. You could even go so far as to say physics is the study of everything, okay? We do say that physics is the most comprehensive science. So what this means is that all the other hard sciences, hard here being in contrast to soft, a soft science typically, things like sociology, psychology, anthropology, those are considered soft sciences. The hard sciences are things like biology, spelled that wrong, biology, chemistry, and the fancy word for earth science, which is geology. Those are considered the hard sciences. And that doesn't mean that they're harder than the soft sciences. It's kind of an unfortunate phrase that originated a long, long time ago. But things where you have physical things that you're manipulating in the real world, those are the hard sciences with quotes around it. Again, doesn't mean the difficulty is any greater. But anyways, physics is the most comprehensive science. All the other hard sciences, biology, chemistry, and geology, they all have physics principles at their core. Why do certain elements bond with each other to make chemical compounds? At its core, you're dealing with physics there. Geology, the study of Earth's history, okay? All the forces shaping Earth into what it is, that at its core is physics. Biology, all the complicated interactions that occur between cells and parts of cells, at their core, those are chemical reactions, and chemistry is really all just physics, okay? So physics principles are at the core of everything. That's why we say that physics is the study of the entire natural world. It's us trying to figure out how the world around us works. And in order to do this, physicists will conduct experiments, and most importantly, physicists measure things. Okay, that's the mark of any scientist, really, is that they measure things. Sometimes people say that like real scientific thought started with the Greeks. They started thinking about kind of questions that we might call it today natural philosophy. They were wondering why things were the way they were. And it is true that the Greeks thought a lot about topics that we might consider science and physics in general, but the Greeks weren't really scientists. The Greeks weren't really scientists because they didn't measure things. The Greeks kind of sat around and observed things and then came up with explanations for why something happened, but they never went and backed up any of their ideas with experiments. It took a long time for humans to start doing that. Really, we didn't really start systematically doing that until probably 500 years ago. In about the 1500s is when you start hearing about the scientific revolution, right along those times. So this idea, the practice of science, really hasn't been around that long, okay? So physicists measure things. We do experiments, and in those experiments we measure things to see if we can confirm our suspicions about something, to see if we can to see if by measuring and doing these experiments we can understand what's happening, and even more importantly, predict what will happen in the future. The three main measurements we're going to focus on for now at the beginning of the year are a meter, which measures distance. Okay, I kind of did this a little bit out of order. We're going to focus on distance measurements, mass measurements. By the way, I'm going to put in parentheses, not weight. Mass and weight are different things, which we'll get to later in the year. and time. We're going to focus on measuring distance, mass, and time. Okay, 3 very simple things, measurements that you've made plenty of times. As far as distance goes, typically we're going to be measuring in meters. Okay, you might sometimes measure in centimeters. We're not going to measure in yards, feet, or inches, or any of that stuff. We're going to measure in meters. We're going to use the metric system. A stumbling block for a lot of people is, well, okay, I know how big a foot is, kind of. I've seen rulers all the time. How big is a meter? There's a lot of things that are about the size of a meter, okay? A baseball bat is close enough to the size of a meter. A golf club is about the size of a meter. A field hockey stick is about the size of a meter. Your arm from your fingertips to your chest to the center of your chest is more or less. Okay, I'm not saying exactly a meter. It's more or less a meter. Okay, there's a lot of things that are more or less a meter. Any of those are a good example. So if I say meter, if something is 3 meters long, you can think in your head, okay, that's about 3 golf clubs. Okay, that's 3 arms lengths. Okay, so you've got to have in your head, if meter's a little unfamiliar to you, pick something that's about a meter long, any of the examples that I just gave, and fix that in your head. This is what a meter is. The measurement of mass we're going to be dealing with is a little bit funny. I'm going to put in parentheses kilo. The base unit is a gram, but we're going to be focusing on kilograms because a gram is very, very, very small. A gram is like the size of a paperclip or a staple. It's extremely small. A kilogram is a little bit more on our scale. A kilogram is perhaps maybe the mass of a textbook, okay, your standard textbook that you might get in a class. Fairly big book, fairly thick, okay? Another good example of a kilogram, and I'll pass around a kilogram, and you guys will see kilograms, kilogram masses that we use throughout the year. A full water bottle, more or less a kilogram, okay, if you got a nice, not disposable one, like a nice metal water bottle like I have right to my side here. Okay, so we measure distance, typically in meters. We measure mass in kilograms. How do we measure time? Now, you guys aren't really used to measuring in meters or kilograms, but you are used to measuring in this unit, which is the second. Okay, meters and kilograms are the metric versions of what I guess we would call feet and pounds. We use the metric system, so we're not going to deal with feet and pounds. We're going to deal with meters and kilograms, but there is no such thing as metric time, or at least not that we're going to use. Time is pretty universal. So we're going to use 1 second as the standard unit for time. The size of 1 second is approximately, let's say, 1 heartbeat. More or less, you have about 1 heartbeat per second. If you don't have something, or don't have a heartbeat of about 1 per second, that's fine. We're not trying to say you have exactly this much, we're not saying that 1 heartbeat is exactly 1 second. We're saying it's approximate, okay, on the order of 1 second. Pretty close to 1 second. Okay, so those are 3 very simple measurements to make. If we just had these tools allowed to us, if we just had a baseball bat, a textbook, and 1 heartbeat, we would get pretty close in all of our measurements to how big or how fast or how quickly or how much mass something has. Okay, these are all pretty good approximations of their units. There's some more units that will come up later in the course, such as the units of current, which are amps, the units of temperature, kelvins. But for right now, we're just going to focus on these, okay? We're going to also focus on combinations of these units. Now that we're done talking about units, I want to go into scientific notation, because in order to be successful in this class, you have to understand scientific notation. You learned this back in probably about 7th grade or so. And when you use scientific notation, it's not something designed just to mess you up. It's something designed to speed up your comprehension, your learning process, and your writing process, okay? Scientific notation is just a much simpler way to write and understand very small or very large numbers. So for instance, this number right here you might have seen in chemistry class, 6.02 times 10 to the 23rd. 6.02, that doesn't seem that crazy, but times 10 to the 23rd is a little weird. What that times 10 to the 23rd tells you, it tells you to take that 6.02 and multiply it by the number 1 with 23 zeros after it. So if you want to write that out, it would be 602 and then like about 20 or so zeros following that. I don't have time to write all that out. So instead we use scientific notation. Okay, scientific notation makes it much easier to write that very quickly. You have to be fluent with going back and forth from what I call standard notation, which would be writing 602000000 and all the zeros, and then going from standard to scientific and scientific to standard. Let's go from standard to scientific first. If you see a number, we have some examples down here that I'll do in just a second. What you're going to do is you're going to take the decimal point so that the number shown is between, or you're going to move the decimal point wherever it happens to be so that the number shown is between 1 and 10. You're going to write that number with a times 10 next to it, and then however many spaces the decimal point moved becomes the exponent on the 10. If the decimal point moves to the left, the exponent is positive. The decimal moved right, the exponent is negative. So let's see how this works. We have this number, okay, so let's see, we have, if I'm reading this right, 299,700,000. Now you might say, well, there's no decimal point there. Well, there is, but we just didn't draw it in. It's really right here. If we want to move this, right now the number, like I said, is 299,700,000. If I move it over once, okay, and now I say it's here, now I just have 29,970,000. Move it over again, I've got 2,997,000. I keep moving this over and pretending the decimal is there, and the number keeps getting smaller. I move it over until I get to here, where this would read 2.997, followed by a bunch of zeros that don't really matter. Okay, that's between 1 and 10. Now I look at this number, 2.997. I'm going to leave off those, the trailing zeros. I guess you can leave those off in this case. I'm going to write times 10, and I'm going to count how many spaces it moved. 1, 2, 3, 4, 5, 6, 7, 8. So the decimal moved to the left. I'm going to put a positive 8 as the exponent. Okay? This was a really big number. Notice that it has a positive exponent, 2.997 times 10 to the 8th. Let's do the same thing with the one below, 0.000000957. I'm going to move that decimal point so that it comes over here. So it's 1, 2, 3, 4, 5, 6. So I have 9.57 times 10 to the, let's see, it moved to the right, so it's negative 6 spots. Notice this number was really small. It has a negative exponent. Big numbers have positive exponents. Numbers that are larger than 1 have positive exponents. Numbers that are smaller than 1 have negative exponents. Okay? Notice also that a negative exponent does not mean a negative number. It means a number smaller than 1. Let's just do the rest of these very quickly. 470. Let's see, decimal point would be right there. Move it twice. I have 4.7 times 10 to the positive second. We don't even really need scientific notation for that one, if we're being honest. I also recommend, if this is too easy for you, which it probably is, pause this, do these on your own, and then come back and look at the, and come back and make sure that you're right. 0.256, that's an easy one. Move it over once. So now it's 2.56 times 10 to the negative first. 38,502. 1, 2, 3, 4. 3.8502. That I'm not going to round because it's not just zeros at the end. Times 10 to the 1, 2, 3, 4th. 170,000. 1, 2, 3, 4, 5. 1.7 times 10 to the 5th. 0.000333. 1, 2, 3, 4. 3.33 times 10 to the, let's see, negative 4th. And the last one, we've got, looks like 5 million. 1, 2, 3, 4, 5, 6. So that'd be 5 times 10 to the 6th. Remember, another way you can read these is 10 to the 1st is really 1/10. So what's 1/10 of 2.56? I take 2.56 times 0.1, and I get that number back. 3.8502 times 10 to the 4th. 10 to the 4th is, let's see, 10,000. So if I take 3.8502, I multiply by 10,000, I get that number back, okay? On the other hand, when we're going from scientific to standard notation, if the exponent that you are looking at is positive, then the decimal moves to the right. This is actually the reverse of what it was when we were going from standard to scientific, which makes sense. We're going the other way, so we're moving the decimal points the opposite way. If the exponent's negative, the decimal moves to the left. That makes sense because by moving the decimal to the left, you're making a smaller number. By moving the decimal to the right, you're making a bigger number. So the first one, 6.67 times 10 to the negative 11th. So this is going to move to the left a whole bunch of places, 11 places. So I'm just going to write, let's see, I'm going to start with 667. I'm going to put a whole bunch of zeros before this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see if that's enough. Starts here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that number is 0.0000000000667. That's a 0, a decimal point, followed by 10 more zeros, and then the 667. Okay? Much easier to write this than to write this, but you should understand how to go back and forth between them. Maybe something a little easier, 1.025 times 10 to the 5th. So I'm going to write my original number, 1.025. It's a positive exponent, so I'm going to move the decimal place right 5 times. 1, 2, 3. I'm going to have to add some zeros in. 4, 5. So that's 102,500. Matter of fact, if I do that on the calculator, you'll see that it comes out to 102,500. And I'll talk more about the calculator in just a second. 8.99 times 10 to the 9th. That would be 8.99. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to add in zeros. So that should be, let's see here, 8,990,000,000. Okay, so at 899 followed by 7 zeros. 1.26 times 10 to the negative 6. Start off with 1.26. Again, I'm going to put a bunch of zeros in here. 1, 2, 3, 4, 5, 6. So that's 0.000000126. 2.5 times 10 to the negative 3rd. 2.5. 1, 2, 3. 0.0025. 5 times 10 to the 4th. I'm going to write my 5. Move my decimal point. 1, 2, 3, 4. 1, 2, 3, 4. 50,000. 9.5 times 10 to the 0. Remember, 10 to the 0 just means 1. So this is just going to stay 9.5. And finally, 2.743 times 10 to the 2nd. I don't have to add any zeros for this one. It's just 274.3. Okay? So it does take a little bit of practice to write out the scientific notation, and it does get a little messy. If you have in scientific notation you're trying to write in standard, it does get a little messy sometimes, but it's something you should know how to do. Okay? Write out the number, add zeros as necessary, move the decimal point as many times as the exponent tells you. If it's a positive exponent, move the decimal to the right. If it's a negative exponent, move it to the left. Some quick tips with scientific notation. We've kind of gone over this one already. Positive exponents are big numbers. Negative exponents are small numbers. Big numbers in this case means anything over 1. Small numbers in this case means anything under 1. Learn how to type scientific notation into your calculator so that you do not have to think about it. Know which button to push to type in the exponent. Remember to include a negative if it's needed. So, for instance, if I want to type in 2.5 times 10 to the negative 3rd on my calculator, I know that I have to do... Oh, got out of focus there for a second. I know that I have to do the following. 2.5 times 10 to the... Now, my calculator is an EE button. You should be familiar if you have an EE button or something similar. I press that, and I type times 10 to the negative 3rd, and it gives me exactly what I need. So knowing how to use your calculator is very important. And then finally, a lot of times on questions you will see the Regents just add in scientific notation for not to be tricky necessarily, but for something for you to do. Even if it's a small number with an exponent less than 5, or so I guess anything that is like 5 or negative 5 and closer to 0. In my opinion on that, you should, instead of trying to type into a calculator, just convert it to standard notation and make sure to check your work. you'll be less likely to make a mistake if the number's in a format you're familiar with. So scientific notation is great for numbers like this, and this, and this, where it takes a long time to write it out. But 1.025 times 10 to the 5th, it really doesn't take that much longer to write this out, okay? I'm not saying it's bad to put this in scientific notation, or this, or this, or this, or this, but if it is hard for you to understand what that means, feel free to convert it to standard notation, which is why you have to know how to go from scientific to standard, okay? And it's also important to know how to go from standard to scientific, just so you can be fluent. All right, I think that's all I've got for this one. We'll come back and talk about metric prefixes in a little bit. Bye.